Hey everyone, and welcome. Today we are diving headfirst into something that's, well, pretty much fundamental to all of physics. It's the concept that explains how things change their motion all across the universe. We're talking about acceleration. So yeah, let's get into it.
So let's start with a little riddle. What do these three things have in common? You've got a roller coaster hurtling down a track, a lizard that goes from zero to a full-on sprint, and a car that's just turning a corner. They seem completely different, right? But I promise you by the end of this, you'll see how they're all connected by one single powerful idea.
So here's what we've got on tap. We're going to start by busting a really common myth about what acceleration even is. Then we'll get into the math behind it, check out the tools physicists use, and then connect it all to Newton's famous laws. We'll even solve a problem together before we zoom out and see just how universal this whole concept really is. All right, let's get right into it. Now, most people hear acceleration and they immediately think speeding up, right? But that's only one piece of a much bigger puzzle. The real secret, the key to understanding all of this, is a little something called velocity. Okay, this is a really, really important difference, so let's break it down. Think about your car's speedometer. It just tells you a number, right? 40 kilometers per hour. That's your speed. But for physicists, that's not the whole story. They care about velocity, which is a vector. That's just a fancy way of saying it has both speed and direction. So 40 kilometers per hour east, that is a velocity.
And that right there is the key to the official definition. Acceleration isn't just about changing your speed, it's the rate of change of your velocity. So if your velocity changes, in any way at all, you, my friend, are accelerating. And boom, this is it. This answers our big question from the beginning. The roller coaster is speeding up, so its velocity is changing. That's acceleration. A car hitting the brakes is slowing down. Its velocity is changing. That's also acceleration. And the car turning the corner, even if the speedometer doesn't budge, its direction is constantly changing, which means its velocity is changing. So yes, it is absolutely accelerating. All three are doing it. Okay, so we get the idea of acceleration, but how do we actually, put a number on it? Let's look at how we can start measuring all this motion. So here it is, the workhorse formula for average acceleration. That little a is what we're solving for. You just take where you ended up, your final velocity, and subtract where you started, your initial velocity. Then you divide that whole thing by how long it took. Simple as that. The units usually end up being something like meters per second squared. Let's put this formula to the test with our roller coaster. Say it starts the drop going a pretty tame 4 meters per second. But just 3 seconds later, it's flying at 22 meters per second. We just plug those numbers right in. 22 minus 4 gives us 18. Divide that by 3 seconds, and what do you get? You get an average acceleration of 6 meters per second squared. See? Not so bad. All right, that formula is fantastic for simple cases, but what happens when things get a little more complicated? Well, physicists have a whole toolkit for that. Let's open it up and check out the famous equations of motion. And this toolkit goes by the name SUVAT. It's basically an acronym for the 5 main characters in any story about motion. We've got S for displacement, which is just distance in a specific direction. U is our initial velocity, V is our final velocity, A is acceleration, and T is time. Pretty much everything we've talked about so far. And here they are, the 5 powerhouse equations. Now, the really cool thing about these is how they're designed. See, each one leaves out one of the 5 SUVAT variables, and that's their superpower. It means if you know any 3 pieces of the puzzle, you can always find the right equation to help you solve for a 4th. It's an incredibly versatile toolkit. Okay, so we spent a lot of time talking about how things accelerate, but we haven't touched on the biggest question of all. Why do they accelerate in the first place? What's the cause? For that, we need to bring in the legend himself, Sir Isaac Newton. And the answer is surprisingly simple, yet it changed everything. An object's motion won't change unless you give it a reason to. If all the forces pushing and pulling on it cancel each other out, it'll just keep doing what it's doing. To make something speed up, slow down, or turn, you need an unbalanced force, a net force. Which brings us to probably the most famous 3 letters in all of physics. F equals ma. Force equals mass times acceleration. This little equation is so powerful. It tells us pretty clearly 2 things. First, if you push or pull harder, increase the force, you get more acceleration. Makes sense. But second, the more massive something is, the more stuff it has, the harder it is to get it to accelerate. That resistance to change is called inertia. Okay, theory time is over. We've got the concepts, we've got the formulas, we've got Newton's law. Let's put it all together and tackle a real problem.
Whoa, okay, I get it. A diagram like this can look pretty intense when you first see it, right? You've got a big 120-kilogram box and two different forces yanking on it from different directions. But trust me, we have all the tools we need to solve this. We just have to take it one step at a time. All right, first things first. We've got forces pulling in different directions, so we can't just add them up. We need to figure out what the total, or net, force is. The easiest way to do that is to look at the horizontal and vertical forces separately. Horizontally, that's the x-axis, we have a force of negative 220 newtons. And vertically, on the y-axis, we've got 150 newtons. Now, to combine those, we can use a little something you probably remember from math class, the Pythagorean theorem. That gives us our overall net force, 266.3 newtons. Perfect. Now we go back to our good old friend F equals ma. We just shuffle it around a bit to solve for a, so acceleration equals force divided by mass. And when you run the numbers, bam, there's our answer. The object is going to accelerate at 2.2 meters per second squared. By breaking it down, we can see exactly how those combined forces create that one specific acceleration. It's not so scary after all. All right, we've been deep in the weeds with formulas and diagrams. Let's pull back and look at the big picture again, because this stuff isn't just for physics class. So when you walk away from this, what are the key things to remember? First, and most importantly, acceleration is any change in velocity. Speeding up, slowing down, turning a corner, it's all acceleration. Second, it's always caused by a net force. Remember, F equals ma. Third, we have a whole bunch of tools we can use to calculate it. And finally, this is not some abstract idea. It's happening all around you all the time. And when I say it's everywhere, I mean it's literally everywhere. You know that famous story about Newton and the falling apple? That's a story of acceleration. The moon orbiting the Earth is only possible because it's constantly accelerating towards us. That's what keeps it from flying off into space. It's the engine of motion in our universe. So I'm going to leave you with a little something to chew on. We know for a fact that if you drop a ball here on Earth, it accelerates downwards at about 9.8 meters per second squared. So my question for you is, what specific force is causing that constant acceleration? And if it's always accelerating, does that mean its speed just keeps going up forever and ever? Or is there some kind of speed limit? Think about it. Thanks for watching.